All right, previously we discussed the 5 basic ideas that everyone needs to understand about physics, and they are matter, energy, forces, space, and time. And right now we're still covering matter. And as we saw previously, John Dalton reignited interest in the atomic hypothesis back in the 19th century, around the early to mid-19th century. This was an idea that was some 2,000 years old, but old habits really die hard. Most scientists were not accepting the idea of atoms as being real things, even during this period. But the case was gradually being made. A guy comes along by the name of Dmitri Mendeleev. And Dmitri Mendeleev he noticed what he called the periodicity of elements. There is a greater interest at this time in greater accuracy and precision of measurement. And it was Dmitri Mendeleev who began to notice that there was a correlation between the masses of certain elements and their physical properties, like the glitter of gold, or the conductivity of certain substances, or how well they reacted with other substances. And so he gives us this early version of what would later be called the periodic table of the elements. There were a lot of gaps in that periodic table, but future scientists would gradually figure out what elements fit in those gaps and would give us today what we now have as the periodic table of the elements. You'll also notice that in Mendeleev's table that there were, as we began to fill in the gaps, it became apparent that if you look at the rows, the ascending order is the atomic masses. This was not well understood at the time as to why, because the actual makeup of atoms was not well understood. But we did know that there were these specific elements, and that their differences were in their masses, which we see in the rows, and their physical properties, which are typically listed in their columns. And we'll notice, for example, we have the most highly reactive substances, chlorine and fluorine and so forth. But next to that is another column of what we call the noble gases. And the noble gases are these elements that don't interact or react with anything. They are inert, and hence the word noble. That's the term they're given because they don't interact with anything else. They're elite. They're above all the other elements. They don't interact well with other elements. But the question as to why were they like that? That was still not well understood. So gradually the case was being made for the existence of atoms. The thing to understand here is that this greater interest in precision and accuracy of measurement required new mathematical tools, which didn't previously exist before, say, Galileo and Newton. So the mathematics was greatly improved during this time. The problem was that old habits die hard. No sooner were atoms actually discovered in Cavendish laboratories in Cambridge, England, then it was discovered that they were comprised of still smaller particles. Now, many scientists at the time sort of already knew that atoms had to be somehow smaller. They had to be simpler substances. But the simplest substance was hydrogen. And so the thinking was that everything just really boils down to just being like hydrogen. J.J. Thomson from Cavendish Laboratories, he discovered that there were particles still smaller than even a hydrogen atom, and these are electrons. He essentially established what's called a cathode ray tube, which is actually the precursor to the modern television. And this is an important point, is that a lot of pure science in the pursuit to understand the origins and nature of the universe, as we pursue those things, the techniques that researchers use often spin off popular technologies. Or we would not have the television of the 20th century, the cathode ray tube. We would not have that were it not for this research into the nature of atoms. So J.J. Thomson essentially discovers electrons are part of atoms. And he gives us this, what he called, from this research, this idea of what's called the plum pudding model, where you have a sort of a mixture of positively and negatively charged particles that make up the atom. But it was actually J.J. Thomson's protege, Ernest Rutherford, who gives us the more modern idea of a nucleus, a positively charged nucleus, surrounded by a cloud of electrons. Now, what Ernest Rutherford did was he set up a target, a gold foil target, and he had a source, a radioactive source of alpha particles. At that time, alpha particles, they didn't know what they were. Turns out that they were later discovered to be helium nuclei, which is just 2 protons. And so these alpha particles would hit this target, this gold foil target. They would tend to go straight through it, like it was nothing. They would just go straight through the gold foil. But occasionally, they would deflect in one direction or another, and rarely, more rare still, they would actually come back at the source. And this was surprising. He characterized this as the same as if you had taken a .50 caliber shell and fired it at tissue paper only to have it bounce back at you. But these experiments that he conducted yielded the idea of a very tiny nucleus surrounded by a cloud of electrons. The electrons being 1,000 times smaller, and we learned that from J.J. Thomson. But what was really strange here is that they discovered that the atom is mostly empty space. You have this very tiny nucleus surrounded by a cloud of electrons, and it's mostly space between them. Now, it's important to understand that when we get down to the size of a typical atom, we're talking about 10 to the negative 10 meters, which is also known as an angstrom. And when you get down to that scale, when you get down to that size, the physics of the classical physics of Galileo and Newton doesn't apply anymore. And so Rutherford gives us this planetary model. But if this is we think of the planets, right, where the sun contains most of the mass in the solar system, and then the planets just kind of revolve around it. And so we get this basic idea of atoms as well, that the atom is kind of a planetary model. The problem is that classical physics would say that the electrons would just immediately spiral inward to the nucleus, and you would have this collapse of the atom. But it doesn't happen. It does not happen. So what's going on at this scale of size and distance? No one knows. This really sort of heralds the introduction of a new physics, but is not really understood at that time. They don't really understand it at that time. This is very difficult because now we're getting down to a scale of size and distance where the physics that makes sense to us doesn't work anymore. So in part 3, we're going to talk a little bit more about atoms, about matter, but we're also going to introduce the new ideas of energy and forces.